Hi guys, in this video I'm going to talk about WebSockets in detail. So before understanding what WebSockets are, let's first understand why they are important for a trading company or from the interview perspective of a trading firm as well. The thing is that a lot of trading companies have now started doing crypto trading. I mean, a lot of trading firms, they have good presence on major crypto exchanges like Bybit, Binance. I mean, when FTX was there, a lot of trading firms traded there as well. And there are other crypto exchanges as well. Deribit, KuCoin and all of that. So the thing is that majority of crypto exchanges, they provide to facilitate automated trading, they either provide HTTP REST APIs or they provide WebSocket APIs. I mean, some trading firms also provide some other different protocols, like Fix protocol is common in some crypto exchanges. So that is why like WebSockets are important to understand if you are involved in the crypto trading space. If you're not in crypto trading space, then you might not encounter WebSockets in your entire career while building exchange connectivity applications. But for any firm which is doing crypto trading, WebSockets might be very important because, as I mentioned, that crypto exchanges, majority of crypto exchanges, they provide either HTTP REST APIs or WebSocket APIs to do order entry or market data or listen to market data. Now, even in some of my interviews, when I was recently interviewing, when I was on a job hunt, like people have asked me that what WebSockets are, how they operate under the hood. I mean, that I think might be also because I had mentioned a few things about building crypto order entry applications in my resume. But yeah, as I mentioned, they are important from the perspective of crypto trading. So let's jump into it. And yeah, let me also give you a couple of examples. Like I've opened the website of Bybit, which is a very major and renowned crypto exchange. So if you go to this Explore API docs, you can note the URL here. If you click on this Explore API docs, it would take you to this link where they have given the documentation of their API. Okay, so here you can see that they provide, different ways to listen to their data or to do order entry. Like they provide REST APIs and they also have a WebSocket stream. Now in the WebSocket stream, you can see that, let's say if you want to get the status of your orders, the orders which you had entered, real-time statuses, they have mentioned here that you can listen to this topic. And in this connect tab of this WebSocket stream, they have mentioned the WebSocket URLs to which you should connect to. Bybit provides different asset classes like spot, USDT, USDC, perpetuals, inverse contracts and options. So each of them has a different WebSocket URL. You connect to that URL, and on that URL, then depending on which particular stream you are interested in or topic you are interested in, you can hear that. For example, I have opened the order topic where they have provided that if you're listening to this topic, you will get real-time updates about your order, and this is the response which comes in. So the WebSocket response sent by Bybit usually only comes in JSON format. So here they have listed the JSON format as well, like a sample response is that for this symbol, this was the order ID, it was a sell order, it was a market type order, this was the price, quantity and all of that, right? And similarly, they have this another topic, you can say, where you can get real-time updates about the orders which are getting filled, your orders which are getting filled. Again, they have mentioned the topic to which you can connect the response parameters which you would get, right? And this is how the response looks like. For example, here you can see that for this particular symbol, this was the execution ID, this was the price at which your order got executed, this was the quantity which was filled, all of that. Okay, so as I mentioned, and if you check the websites of other crypto exchanges as well, like Binance as well, you will see that they also provide WebSocket stream. And this was mostly for listening to order updates. They also provide you updates about market data on WebSocket. For example, you can listen to the depths. You can receive the order book depths, which is for market data on this particular topic. The topic is this one, orderbook.dep.symbol, and this is how the response would look like. So as I mentioned, this is why WebSockets are important if you are involved in crypto trading. So now when you are writing any application like a trade server or a market data or order entry application, in general an exchange connectivity application for a crypto exchange, And let's say if you're writing it in C++, you can either use pre-existing libraries in C++ which provides WebSocket capabilities, or you can implement the WebSocket protocol yourself. So in my previous company, we had implemented the WebSocket protocol ourselves, and I was also involved in some parts of building exchange connectivity applications for crypto. So I also got a chance to read that implementation in C++, and that is when I read the entire WebSocket protocol and got familiar with it. And the implementation was very well written. So let me describe you how WebSocket works in detail. Okay, so let's look at the WebSocket RFC. So every protocol which is developed, like WebSocket, HTTP, TCP, UDP, all of that. So there is this organization called Internet Engineering Task Force, which publishes the specifications about that protocol, and they publish it in RFCs, which is called a request for comments, and each RFC has a unique ID. Okay, so here they have described the entire WebSocket protocol, and this is what everyone follows when they are implementing it. Okay, let's say if any library developer who is implementing a WebSocket library, like they will read this protocol and they will understand it and basically implement it. You are required to follow the things mentioned in this particular protocol. So let's see how WebSocket basically works. So the thing is, and yeah, before diving into WebSocket, let's see why they were required. What were the use cases which cannot be solved using WebSocket? Which basically created the essence for WebSockets. So if you look at this picture, like you are doing client communication between client and server. So to get all these order updates and all of that, one way of communication can be that you send HTTP request, REST API request, and you will receive the response for your order books or for your order updates, right? But there was a problem with those kind of things. The thing is that HTTP is usually not suitable for doing bidirectional communication. By bidirectional communication, I mean that when client is also sending data to server, and server is also sending data to clients. There are ways to communicate it. For example, let's say you are building an instant messaging or a gaming application. You can exploit HTTP, and people have done that. They do continuous polling of HTTP servers, but those kind of things create problems, and they have written like a few problems which comes with that. Like one of them is that sometimes a server might be forced to use a number of different underlying TCP connections for each client, and one TCP connection might be just for sending information to client, and one can be for receiving information from the clients. Similarly, like for every HTTP packet which you would send, the HTTP header creates an overhead on the network, right? And another thing is that if a server is maintaining different TCP connections for outgoing and incoming messages, then client side is also forced to follow that, and for that it would then need to create a mapping of outgoing and incoming connection to figure out that the response which it has received belongs to which particular request it has sent. So as I mentioned, for heavy bidirectional communications, like for example, the one which happens in gaming applications where server is continuously sending updates to clients, or even in instant messaging applications, HTTP is not a very good protocol which you could follow. So these kind of issues which were there with HTTP and which cannot be solved, which created problems for bidirectional communications, this WebSocket was created. And WebSocket, basically they are suitable for doing full duplex bidirectional communications. And now let's see like how does basically WebSocket work. The thing is that whenever you want to establish a WebSocket connection, let's say there is a client and a server, they want to establish a WebSocket connection. So the first thing which they need to do is that the client needs to send a handshake to the server. Okay, the WebSocket handshake. The first thing which would happen is that the WebSocket is an application layer protocol, so it uses the TCP protocol as the transport layer protocol. In case you are unable to understand it, so what I mean is that if you recall the 7 layers of OSI model, basically you have at the bottom you have the physical layer, then you have data link layer, then network layer, then transport layer, then there is session layer, presentation layer, and then the application layer. So session and presentation layer are usually not important. So if you just look at this, so WebSocket is the application layer protocol. Okay, in the OSI layer it is level 7. But then what would be the protocols for other layers which it follows? So the protocol at transport layer followed by WebSocket is TCP. Okay, I mean at transport layer you have TCP and UDP protocol, so WebSocket is operated over TCP. Okay, so whenever a client and server wants to do communication using WebSockets, first thing which would happen is a TCP connection would be established between them. So this is the first thing which happens. You establish a TCP connection between client and server. When the TCP connection has been established, now it's time to initiate the WebSocket handshake, the connection handshake. Okay, so the handshake happens like this, that it is basically an HTTP upgrade, a WebSocket upgrade request. Okay, and the format for this is that client will send this this is an example. This /chat is the endpoint, you can say the WebSocket endpoint. Okay, I mean by WebSocket endpoint I mean these endpoints which were there. So the client will send a request like this, I mean the handshake like this, like get, and then this is the endpoint, and then HTTP 1.1. Then it would mention the host name of the server. It needs to send that this is a WebSocket upgrade request. Okay, so upgrade WebSocket. Then it needs to tell that this connection type is upgrade type, and then it needs to send some more information, like this information is not important for us, but these 4 information are very critical. Okay, and I mean this origin is provided in the connection handshake to mention, basically it helps prevent the cross origin reference attack. So these kind of things, this is why it is required. But yeah, the 4 major important things are this, that the connection handshake is basically a GET request over HTTP, and we specify the connection type as an upgrade, and upgrade is for WebSocket. Now when the server receives this handshake, if everything is good in the handshake request sent by client, the server would send a handshake response. The handshake response would look something like this, that HTTP 1.1, then this is a status code 101, then this response, that switching protocols, it would mention switching protocols. It would echo back that upgrade type which was WebSocket, and it would echo back the connection type which was upgrade. And again, these 2 things which can leave for now. So these are the 3 important things. If instead of 101 you receive any other status code, I mean if the client receives any other status code from the server instead of 101, it means that WebSocket handshake was not successful and the connection won't be established. So this is the first step. I mean, after establishing the TCP connection between client and server, the client sends a handshake and the server will reply with that. I mean, in case it is successful, the server will reply with 101 switching protocols. Now when this handshake has happened, now the data can be interchanged between client and server over WebSockets. So as I mentioned, this RFC now describes this opening handshake in detail. Okay, and each of the you can say the fields in the handshake are also described. And one thing to understand is that WebSocket is able to operate on HTTP and HTTPS ports as well. I mean, HTTP port is port 80 and HTTPS port is 443. So the creators of WebSocket protocol, they saw that for client server applications, they decided to provide it over HTTP ports, because you can use other ports as well, but HTTP ports would also work fine, because they kind of wanted some kind of compatibility between HTTP and WebSocket, so that it does not become difficult for people using HTTP protocols to switch to WebSocket protocols. I mean, it should remain easy for them, right? So that is why they decided to do that, and that is why you also see these kind of things in the handshake, like HTTP. We are saying that from the HTTP connection we might be upgrading to a WebSocket connection and all that. Okay, now the thing is, let's skip these parts. I mean, these you can read in the RFC. It describes the opening handshake in detail. And when you are closing the connection, when let's say WebSocket connection was established, then data interchange happened, and now WebSocket connection is getting closed. At that moment, we send a closing handshake. I'll describe the closing handshake later in detail. And now let's jump to how actually data is interchanged between client and server. And one more thing is that these WebSocket URIs, okay, so what they are. So a WebSocket URI, it will basically, for example, if you look at an HTTP or HTTPS URI, how does it look like? You have HTTP : then // then www. some, let's say google.com, then / and then path of any endpoint. Okay. So the WebSocket URL is also kind of same. I mean, WebSocket URL is you can say identified by a prefix of WS colon. In HTTP, it was HTTP colon or HTTPS colon. Similarly for WS, I mean for WebSocket you have WS colon, and for HTTP over SSL or HTTP over transport layer security, we had HTTPS. Similarly, WebSocket can also operate over transport layer security. Okay, so that's why we have a WSS as well. Then you have the standard double hash. Then even in HTTP URIs, we had this host like www.google.com. Google.com was the host. Then we have, if there is a port as well on that host which runs that particular WebSocket application, then a port is also specified, separated by colon. Then you will have path. By path I mean like this path. For example, if you look at this URI, which is an HTTP URI, this you can say is kind of, you can say a host. Then after slash you have the path, right? So similarly, this is the path there, and then you have the query parameters. I mean, it is similar to an HTTP or HTTPS URIs, except the prefix here is WS and WSS. Good. Now we have the handshake is done, and yeah, one more thing, that as we had seen, the fields of the handshake, like it contained fields about get, then there was an endpoint, then it had host name and all of that. So those are determined from this URI only. Okay, that is also one thing to remember. Now let's jump at how the actual data is interchanged. So that is given in the section 5 of this particular RFC. So yeah, this is the RFC. So what happens is that a WebSocket, you can say like a WebSocket packet is kind of a data frame. I mean, the terminology used for that is frames. I mean, data is interchanged in forms of frames in case of WebSocket. So let me give you a bit of a detail about it. So as I mentioned, that WebSocket is an application layer protocol. Okay, so let's say you have a client, I'm denoting client as C, and you have a server. Now let's say this server wants to send some response. Okay, so and these client and server are not running on the same host, they are on different hosts. They might be, maybe even server might be located in United States, the client is in India. Okay, so whatever data which server needs to send to client, it would traverse over a network. So what would happen, let's say, and the mode of communication is WebSockets. So what would happen, that let's say this server wanted to send some JSON response. I have shown you some sample JSON response when I showed you the Bybit API docs. So what would happen, that sample JSON response would be kept in a WebSocket frame. Okay, so this you can say is a WebSocket frame. Now this as I mentioned is at the application layer, because this is the data of the application. This WebSocket frame cannot directly travel on the network. So if you recall the OSI layer, now this WebSocket frame needs to be encapsulated inside a transport layer packet. So if, as I mentioned, that WebSocket operates over TCP, so it would be contained within or encapsulated inside a TCP segment. Now this TCP segment would be enclosed inside a IP fragment, because the protocol at network layer is IP. Okay, so this would be enclosed inside an IP packet, and then this IP packet would be enclosed inside a Ethernet frame, because this is the layer 2 protocol, or at layer 2, I mean only Ethernet frames travel. You can say not on the layer 2, but on the physical link layer, on the actual wire, the Ethernet frames are going to traverse. Okay, so the application data, as I mentioned, that JSON data would be contained inside a WebSocket frame. So why I have explained this entire hierarchy, so this is actually important. This would be important to understand further concepts of WebSocket as well, and it will also give you a bit of a revision about your computer network. So what happens, that whenever server wants to send client some data, like this is, it would eventually create an Ethernet frame and it would send it towards client. Now in between the network, like how does this data reach to client? I mean, this IP address would determine the network or the sub network where this data should reach. When it is arrived in the network of the client, this Ethernet address helps to determine that which particular host has, I mean the Ethernet addresses are basically the MAC addresses of your computers. So this Ethernet addresses determine that this particular host, I mean this MAC address is for this particular host, and then the network interface card would read this packet. I mean this Ethernet address would help this particular Ethernet frame reach the particular host. And on that host, if you have multiple interfaces, which particular interface should be reading this particular Ethernet frame. So IP datagram determined the network in which the client exists. Ethernet address or the MAC address determined the particular host and the MAC interface on which should read this data. Now let's say this client was my computer only. Okay. Now it has this particular Ethernet frame has arrived to my computer. But on my computer, I am currently running multiple applications. Like I'm running this Paint here, I'm running Google Chrome, I'm running OBS Studio to record this particular video, I'm running this Predator Sense software to basically monitor my CPU temperatures, fan control and all that thing. So how would operating system determine that this particular packet or this particular WebSocket frame, this was meant for which particular application? So that is where this TCP datagram helps you. The TCP header has a destination port number, and each application running on your computer has a different port. So this TCP port would tell you that this packet was meant for which application, and finally when this the application reads this particular the application then would only get the WebSocket frame, because your operating system, the kernel network stack of your operating system would have stripped the Ethernet, IP and TCP headers. Now your application would only get WebSocket frame, and now it can read the data. So this is how the data would be communicated from server to client. Now the thing is that there is a limit on the size of these Ethernet frames as well. I mean, there is a concept of MTU, maximum transmission unit. So in the trading infrastructures, usually the MTU is 1500 bytes. So what that basically means that the size of the Ethernet frame cannot be more than 1500 bytes. So you can also imagine now that the data contained inside WebSocket frame is limited only because of this upper limit of 1500 bytes, right? Because this 1500 bytes would contain Ethernet header, IP header, TCP header. I mean, the IP and TCP header are usually 20 bytes. So this comes out to be 40 bytes, and I do not remember the size of the Ethernet frame header right now. So, but yeah, important thing is that the WebSocket frame data is also limited. In one frame, you can only send some limited amount of data. So now coming back to this particular response which I had shown you, let's see here, that was in private and in order. So you can see that this JSON is very big, right? It might be more than 1500 minus that size of IP, TCP and Ethernet frame header, right? So if this is more than, or let's say this is more than 1500 bytes, so you cannot send this entire data in one frame. So what happens that this WebSocket, basically the server would send multiple WebSocket frames. Okay. So what server would do is that it would send multiple WebSocket frame. Let's say WS frame 1. I'm drawing this with blue because I had drawn the WebSocket frame here with blue. So it would send multiple WebSocket frames to this. The server would send multiple WebSocket frames to this client, and each of them would contain some identifier. Okay. So let's now discuss this here in detail. How this data is sent, actually the application data is sent. So what happens that a WebSocket frame looks something like this. It contains some header information. So let's see, I mean the first byte in any WebSocket frame, the first byte would have this fin flag. So I'll explain you what fin flag is later. There are these three RSV1, RSV2, RSV3. You can ignore them right now. They are kind of, you can say, you can ignore them right now. I mean, usually they are not important. Then there is an opcode which tells you the type of this WebSocket frame. We'll also come back to it in later. There is a 1 byte mask which tells you whether this data is masked or not. I mean, this is only, this is not 1 byte. It is, I think, only 1 bit. Sorry, this is only 1 bit. So this can be the true or false, and that would tell you whether this data is masked or not. Then there is the payload length, which tells you the actual length of the payload contained inside it. So by payload, what we mean is that, let's say if this WebSocket frame contained the JSON data, then it would tell you the length of the JSON data contained in it. Then there is this extended payload length, And then you have the masking key. Masking key will only be present if this mask is true. Okay, and then you have the actual payload data. The payload data is that JSON which you are sending. Now let's see what each of them are. So let's see what this fin flag is. So as I mentioned that you cannot, if because of that MTU or other network constraints as well, not just because of that MTU. I mean, on network usually only in one Ethernet frame you can only, there is usually an upper limit on the Ethernet size of the Ethernet frame which you can send, and there can be other reasons as well. Maybe the on the receiver side we are overflowing the receive window, the TCP receive window, right? So in that case also it might be that you cannot send more than this amount of data. So as I mentioned that the data is divided into small chunks of WebSocket frame and then sent. So let's say we sent 4 frames which contain that order JSON. This is the first frame, this is the second frame, this is the third frame, this is the fourth frame. So how would the client, after receiving these 4 frames, know that it has received that entire response, the entire JSON response, right? So the way that is communicated is using that fin flag. If since this 4th frame is the final frame which contains the last part of that JSON, the fin flag, the first fin flag will be true here. So that is what the fin flag for it. It means that this is the final frame. Okay, final fragment in a message. You can ignore this RSV1, RSV2, RSV3 now. Now the opcode tells you that what kind of data it is. Okay, so it can be text data, binary data, it can be a connection close frame as well. So this connection close will come later, but that is used during closing the WebSocket connection. It is used during closing handshake. There is a ping and pong frame. I'll also explain you that, a type of ping and pong frame. But let's see what is this continuation frame. So what this continuation frame is that, as I mentioned, if we are sending these 4 WebSocket frames which contains that entire JSON, so the second, third and fourth frame will have this continuation flag set, because it is telling that this second frame is in continuation with the first frame, the third frame is in continuation with the second frame, and this fourth frame is in continuation with the third frame. So in fourth frame we have both the continuation and final fragment bit set, because it tells that fourth flag was in continuation with the third frame and it is also the final frame. Okay, so this is how, using these 2 information, the client is able to figure out that this JSON is contained inside these all 4 frames, and the client basically will have to buffer the data of first frame after receiving it, then second frame, then third frame, and then fourth frame. Only when it has received all these 4 frames, it can actually see that entire JSON. So on the client side, when you are implementing this particular protocol, you will have to write this buffering logic. Now we'll discuss continuation frame in a bit more detail, but yeah, this is what the opcode is for. That it basically tells you the type of frame. You can have text frame that it contains text data. Binary frame tells you that this frame contains binary data. Okay. The mask, as I told you, it's 1 bit. It is true if data is masked. It is false if data is not masked. We'll also come to it later. So payload length. Now, basically, what is the size of the payload, or what is the size of the JSON contained inside this frame? Again, the payload can not be JSON, it can be anything, but for our example it is JSON, right? So there is a certain logic to basically interpret the length of the payload. So it is that, as you can see, the payload had the payload length and the extended payload length as well. The payload length is 7 bits. So in 7 bits you can see that the maximum number which we can fit is 127, 2 raised to power 7, right? So not 2 raised to power 7 minus 1. So if the length of payload, if this particular payload length, if the number inside it is between 0 and 125 inclusive, then this is the payload length. In case this is 126, then the next 2 bytes, basically the first 2 bytes in this extended payload length, tells you the length of the payload. If this value is 127, then the 8 bytes of the extended payload length will tell you the length of the payload. Okay, so this is how the payload length is interpreted. You can read about it in detail. Now the masking key. Masking key is of 4 bytes. It tells you, basically it is the masking key. We'll come back to it later. Then there is payload data, as I mentioned, and the application data, whatever is the JSON is there. Okay, so let's see now the concept of masking. Basically what masking is. So the thing is that WebSocket tells you that whenever a client is sending data to server, it should always be masked. And if server is sending data to client, it should not be masked. If this is not followed, then the connection would be immediately closed. Let's say if client sends unmasked data to server, then server will immediately close the WebSocket connection. And if server sends masked data to client, then client should immediately close the WebSocket connection. This is what is specified by the RFC. And the masking is basically done for security purposes. Okay, this is why masking is important. And the masking algorithm is and yeah, now you can also imagine that mask flag which we had, it would be true in all the frames sent from client to server, but it would be false in all the frames sent to server to client, because masking is only done for data going from client to server, right? And the way, now this masking key can be anything. In every frame you can, I think, send any masking key, but how would you basically figure out the actual data using the masking key and the data present in the payload? So that is figured out using this algorithm. So the ith byte is actually the XOR of the ith byte in the payload data and the I modulo 4 byte of the masking key. Okay, this is the algorithm used to do masking and unmasking. Now we come to fragmentation. So this fragmentation is explained in this particular 5.4 section, but I have already explained you what fragmentation is. This is what we call fragmentation, basically fragmenting a large data into small fragments and then sending it. Okay, and the way fragmentation is done using continuation and final bit flags. Okay, the final bit flag will tell you that this is the last fragment, and the continuation that continuation frame type, in opcode we had that continuation flag, right? So that tells you that this frame is in continuation with the previous frame. And WebSocket describes that when you are sending the fragment data, basically between continuous frames, you should not send any other data, because let's say between this basically we tried to send two responses. One was that order book response, and let's say one was that execution response. Maybe the execution response had 3 frames, let's say 1, 2 and 3. Okay, let me actually label them as E1, E2 and E3, and these were O1, O2 and O4. O1, O2, O3 and O4. So the thing is that, let's say the server sent frame O1, so the next frame which it should send should be O2 only, because this is in continuation with O1. It should not send E1, or it should not send any other frame in between, because then you can also see that how would client assemble the packets, right? If it receives O1, then after that, let's say it receives E1, then it would think, okay, O1 and E1 are in continuation, right? Or it might think that, okay, O1 was the only data which it has received. So that's why this interleaving of frames are not allowed. So this is what is described in and you can also see why this requirement is essential, because otherwise client would not be able to correctly collect the fragmented frames and create the actual response. Between these fragments, you can only send the control data. The control data is basically maybe kind of a ping or pong frame, which we had seen there. Only the control frames are allowed between the fragments. Message fragments are not allowed. So this is also written here that message fragments must be delivered to the recipient in the order sent by the sender. The interleaving of message fragments is not allowed. This is also written here that the fragment of one message must not be interleaved between the fragments of another message. And this is because, otherwise the client won't be able to collect all the fragments and correctly figure out the data. Now coming to the control frames. So ping and pong are control frames. So why they are used? Because they basically are used to see whether the connection between client and server is still alive or not. Let's say we had a client WebSocket connection between client and server, and let's say for 1 minute they did not have any communication. Okay, server did not send any data to client did not send any data to server. So how would client and server know whether they are connected or not? Maybe server is sending data to client, but it is not reaching to client because there was some network failure in between. Maybe some router between server and client failed. Okay, or maybe the client has crashed. Server is still sending data to client, but the client has crashed. Okay, client is not receiving anything. So to check these kind of scenarios, whether whether basically we are actually not sending any data, or the data is not reaching anyone because the network has crashed, or so to see whether the client and servers are still alive, these ping and pong frames are used. So, and these are only used when there has been a duration of inactivity between server and client. So server can send a ping frame, and whenever you receive a ping frame, you have to reply with a pong frame. So the pong and ping frames are described here, and you can also see that somewhere they had mentioned that they are used to this note mentioned that a ping frame may serve either as a keep alive or as a means to verify that the remote endpoint is still responsive. Okay, and the response to a ping frame is always a pong frame. Now we come to this close frame. What was this close frame? Okay, and again, if you forgot that all these ping, pong, continuation, close frames are determined by the opcode, the 4-bit opcode. Okay, this 4-bit opcode. Now the close frame is that, let's say client and server, they established WebSocket connection, they did some interchange of data, and now everything is done. So the way the WebSocket connection is terminated is that you do a closing handshake. So how it would happen that the client or maybe the server as well, they will send a close frame. How close frame is determined? Using that by setting that close flag in that opcode. And in the close frame, you can also send the reason why you are closing that connection. Maybe let's say a server has sent a close frame to client. In the application payload data, the payload data which is there in the frame, the payload data will tell you, it can contain the reason for closing the connection. Like maybe the server received a very big fragment, right? That is why maybe it is closing the connection, or maybe it received some, you can say, invalid data. Maybe, as I mentioned, that client should always send masked data to server. Maybe the server did not receive masked data, it received unmasked data. So server can send the close frame to do the WebSocket close, connection close. Or maybe client received masked data from server, which is invalid because servers are never required to send masked data. So in that case, the client can send the close frame. And the way basically WebSocket says that if you want to do the connection close, you should do a closing handshake, and the closing handshake is done by sending a close frame. The close frame is determined by setting the close flag in that opcode. Okay, not by setting the close flag in that opcode, but the thing is that the opcode is of 4 bits. So there are different values which you can set in the opcode. Like if the value of opcode is 0, it means that it is a continuation frame. If the value of opcode is hexadecimal 1, it means that it is a text frame. If value of opcode is hexadecimal 2, it means it is a binary frame. Similarly, if the value of opcode, if you want to send a close frame, basically if you want to do a connection close, you send a value of hexadecimal 8 in the opcode. It means that it is a connection close. Similarly, this 9 and A is a ping and pong. Okay, if value of opcode is 9, it's a ping. If value of opcode is A, it means it is a pong frame. So this is mostly about the WebSocket protocol and how the communication between client and server happens. Then there is this section 6, which basically tells you about sending and receiving data, which I already explained you. When you are sending data, you might be required to fragment the data, right? And on the client side, how do you figure out that you have received fragmented data? You basically look at the continuation frames, and if you are getting continuation frames, it means that this particular frame was in continuation with the previous frame. Similarly, you look at the final bit flag. If you received the final bit flag as set, if its value is 1, it means that this was the final fragment. Okay. So you can also see here that, let's say if the entire response only fit in one packet, so the server will only send this one packet and it would set the final bit flag here. Okay, because the final bit flag is set, then client is able to figure out that the entire data is contained inside only one frame. In this case, how did client know that it would receive more frames? I mean, when client received this O1 frame, how did client know that it needs to receive more frame? Because the O1 frame won't have the final bit flag set. Since the final bit flag is not set, the client knows that this is not the final fragment, the final frame, it might receive more frames. Okay, then it received O2, which had continuation, in which the value of opcode was 0, which means that this is in continuation with the previous frame. Similarly, for O3, the value of that would be 0. It means that this is in continuation with the previous frame. And in O4, the value of opcode would be 0 and the final bit flag will also be set. It means that this is in continuation with the frame O3, but this is also the final frame for this particular message. So I mean, in my previous company, we had implemented this entire logic. We had all that buffering logic, and we had these switch cases to determine what kind of opcode which we have received. We checked if it was a final frame, and when we received the final fragment, then we collected all that data. I mean, we took all that data and then created a JSON from it, and then eventually did parse the response. And in C++, to give you additional knowledge, the JSON library which is commonly used is this nlawman JSON. So this is a JSON library for modern C++. This is very heavily used in almost every firm. I mean, I worked in DE Shaw, they also use this. At Tower also they use this. I have worked in some other firm as well as a C++ developer, they also use it. So that is all I had for this particular video. I hope you liked this video. Please do not forget to like, subscribe and comment, and I'll see you all next time.